Hello everybody, my name is Felipe and I will present our paper, Assessing Time-Based and Range-Based Strategy for Commit Assignment to Releases, in SANER 2021. Generally, the release mining initial steps consist of assigning the commits to releases. However, Git and other version control just track the last commit of each release. Hence, stakeholders must adopt a strategy to assign the remaining commits to each release. Depending on the chosen strategy, the release mining may include commits that do not belong to the release, which we call false positives, or it may miss commits that actually belong to the release, which we call false negatives. The wrong assignment may affect the release mining application, such as generating automatic release notes missing features or including features from other releases. It may fetch wrong information by comparing releases, and also lead to searching the wrong code base for bugs. The time-based strategy is one strategy to assign commits. It uses the time to assign the commits. I will exemplify the time-based strategy using a real release from D3.js on the left and the one from Node.js on the right. First, we select a release. Next, we retrieve the timestamp of one of its base releases. Then, we select all the commits made after the base release that are reachable from the release. Let's do it again in the other sample. Retrieve the timestamp of a base release and select all the reachable commits made after this timestamp. The following Git command implements the time-based strategy. On the left sample, I would like to highlight the commit E, because it's not reachable by the release and should not be included. However, an unfamiliar developer may include it by mistake and introduce additional errors to the analysis. The range-based is another strategy to assign commits. It uses reachability. First, we select a release. Next, we retrieve all the reachable commits. Next, we select a base release and subtract all the reachable commits. Let's do it again in the other sample. First, we select the reachable commits. Then, we select the base release reachable commits. Next, remove all the base release reachable commits. The following Git command implements the range-based strategy. In this paper, we answer 3 research questions. RQ1, compare the strategy. RQ2, evaluate 2 factors that may influence the strategy, the number of developers and the number of base releases. RQ3 evaluates the inclusion of an unreachable commits in the time-based strategy. As we explained earlier, it may happen by a mistake with unfamiliar developers. In our experiment, we created a corpus with 100 open source projects, over 13,000 releases, and almost 1.5 million commits. Because there is no ground truth of which commit belong to each release, we devised an algorithm to compare the strategy. We measured precision and recall, and then aggregated the values per project using the macro average mean. Finally, we run statistical tests to compare the releases. The baseline algorithm gets the release and sort them by the time they were released. Then, it gets the first release and assigns all reachable commits. Next, it gets the second release and assigns all the reachable commits that were not previously assigned to other releases. It repeats the algorithm until we arrive in the target release. Let's do it again. Select the first release commits, then select the second release commits, and finally, select the target release commits. The baseline considers the whole project history and identifies the release that delivered the commit for the first time. Now, we can compare the strategy with the baseline, and you can find the false positives and false negatives. Hence, we can calculate the precision recall for each strategy. The sample from D3.js, the time-based strategy found one false negative. The range-based strategy matched perfectly. In the sample from Node.js, the time-based strategy found two false positives and one false negative. The range-based strategy found two false positives. Now, I will show our findings. In RQ1, we compared the strategy. We found that the strategy has similar precision, but the range-based has a higher recall. In RQ2, we evaluated factors that may influence the precision recall of the strategy. We found that the number of developers influenced the time-based strategy recall. The bigger the number of developers, better is the recall. The range-based strategy is not affected by the number of developers. We also found that the number of base releases influenced the time-based strategy recall. The bigger the number of base releases, worse is the recall. The range-based strategy is not affected by the number of base releases. In RQ3, we evaluated the impact of selecting unreachable commits in the time-based strategy. Do you remember the commit E from D3.js sample? We found that including unreachable commits drastically reduced the time-based strategy precision. Finally, our experiment has some threats of validity. We worked with open source projects and we have no control over their development. We select the base release considering semantic versioning and found some semantic and timestamps conflicts in the repositories. We worked with macro average mean, then we assigned equal weight to all releases in a project, dependently of the number of commits. And finally, we studied open source projects with hundreds of contributors. Hence, our finding cannot be generalized to the industry. As conclusion, we assessed the time-based and range-based strategy over a project corpus with 100 open source projects, over 13,000 releases, and almost 1.5 million commits. The range-based achieved better results. Thus, stakeholders in charge of mining release should consider adopting the range-based strategy instead of the time-based. Finally, we implemented an open source tool that mines releases using time-based, range-based, and the baseline strategy. Thank you for your attention.